All right, welcome back. So we've just finished an example here on doubling time, doubling formulas, how long we go every time we double. And another low-hanging piece of fruit on this tree is, well, the opposite of doubling is cutting things in half over and over again. And just the same way that things can grow exponentially, they can also decay exponentially. And usually, the easiest reachable example for a math class such as this one is something that was Half Life, Half Life 1 in this case. And we can make a halving formula much the same way we can make a doubling formula, except now it's going to be 1/2 to a power. And the power here is t divided by 5730. And that's because the half life of carbon is 5730 years, 5,730 years. So if that many years go by, I have half the carbon left. Another one of those 5,700 years go by, I'm down to a remaining half of the half, so I've got 1/4 left. And then another 5,700 years, I'm down to 1/8 left, a half of a half of a half, and so on and so forth. This is very useful in figuring out the age of certain pieces of material that we find under the earth. This is carbon dating. There's also other sorts of dating for other types of elements based on how far back you want to go. But we found a fossil, 72% left. We want to know how old the fossil is. And so the way we'll do that is use our equation here. P is our starting amount. That's 100%, which I'll write as 1. A is the amount left. That's 0.72. And then I will solve for t much the same way that I solved for t before when I was trying to find out how long I had to work. What we'll do here is we will take the appropriate logarithm, and you'll recognize the base of this exponential is base 1/2 or base 0.5. You can do it either way, right? They mean the same thing. So we take that logarithm, base 0.5, so that the right-hand sign cleans up real nice. And I am left with t being 5,730 times the log with a base of 0.5 of 0.72. And that comes out to be about 2,700 years old. And that is really how the math behind carbon dating and other dating techniques are used with half-lives. So that's pretty neat. And if you don't think it's neat yet, don't worry. This was Half-Life 1, so I've got Half-Life 2 coming up. Don't worry, we won't do more examples than that because there is no Half-Life 3. And I know that aged like milk with the recent release of Alex, but anyway, it's going to work out for us that the doubling and halving formulas are actually a smaller piece to a bigger picture, which is all the different things we can do with growth and decay. Right? Growth, exponential growth, be it populations, money we're making, also loan debt, student loan debt, money we owe also grows exponentially. If we want to be a little more on the nose here, whenever there's a infection spreading, the number of people who are infected grows exponentially. And also, if you want to be a little mean to some of your older friends on Facebook, you can also talk about why multi-level marketing schemes are unsustainable, again, using exponential growth. Other models, of course, Half-Life. What happens if you make minimum payments on a credit card? That can be growth, exponential decay. Reverb and acoustics, that was something I worked on in my undergraduate studies as an engineer. Those things have exponential decay of them. And also, if you want to be more like a CSI, estimating time of death, sometimes you can use decay models for that as well. Exponential decay models there, sorry. All right, so whichever application you're working with, be it finances, people, whatever, the general model has E as the base, has E as the base. And so I've got here for you all the different notations that we need for this formula. So I'll leave it on this slide here for the rest of the video. But to talk you through it real quick, A is the amount at the end, P is the amount at the start, E is 2.7, R is your growth rate, and T is your time. Now, if your R is in percent per year, T needs to be in years. Those units have to agree. And we'll do some examples in the next video. See you then.